Okay, I guess we can go ahead and get started. So we're respectful of everyone's time. Thanks for joining us. In this Build L2 workshop, we have Pablo, and I'll let him introduce himself here in a bit, but we're just going to discuss the new open sourcing of the functionary code and give a bit of some background, discuss what a liquid functionary is, so you have a little bit more context as well. And then Pablo is going to demo how to create your own liquid-like network using elements and the newly open-sourced functionary code. So thanks for joining us, Pablo. If you want to intro yourself and discuss your role at Blockstream and everything, that'll be great.
Yeah, hello. Yeah, my name is Pablo. I'm the engineering manager of the Liquid team, and my role is mostly being in the middle of all the developments that are happening in the functionary code, in the elements code, and the involvement with the Liquid Federation and with Blockstream as a technical provider for the Liquid Federation. So normally, yeah, it's up to me to do the final stages of controlling what goes on to the functionaries. Basically, the Liquid Federation is an 11 out of 15 multi-sig that controls the funds on the Bitcoin side, and the same 11 out of 15 multi-sig is used to create the blocks in the elements sidechain. What we are gonna do today is a bit of an oversimplification of that. We are gonna create a 2 of 2 network to make it simpler, and I have a few commands ready to be executed, and we are going to start with an empty container and download the code, compile it, and create a 2 of 2 network, as I mentioned, running exactly like a functionary would run. So in order to do that, let's go back a bit. What is a liquid functionary? A liquid functionary is composed of several different parts. First of all, it has a Bitcoin full node because it needs to validate all the transactions that happen on Bitcoin in order to understand which of those transactions belong to the federation. It has an elements full node because that's where all the liquid transactions happen, and where the blocks are produced and everything. That is what used to be open source up until now. Obviously, Bitcoin and the elements source code that is the underlying layer for the liquid chain. What we released last week is mainly the 2 tools that work on top of that. The first one is Block Signer, which is basically the tool that coordinates the signature of the unsigned blocks that are produced by elements. So how does this work? In a round-robin fashion, each of the 15 functionaries, they ask elements for a block that is generated unsigned. If you try at that moment to add the block to the chain, elements would reject it because it doesn't match the 11 out of 15 signatures required. So it distributes the block among all the other functionaries. Everybody sends their signatures, then the signatures are collected and then added to elements again. At that point, elements can confirm that the signatures match with the validation that it has configured, and it accepts the block into the chain. Once that block is accepted, it's broadcasted to everybody, to all the nodes that are actually connected to the Liquid network. What does Block Signer do with regard to the block? basically not much. With regard to transactions, it doesn't do anything. It doesn't touch the transactions. What it does add is some of the header fields, mostly to prepare for DynaFed transition. DynaFed is short for Dynamic Federations. And it's something that allows the set of signers to be changed. And let's leave it at that for now, because that's a too long explanation. But we could do a deep dive in DynaFed at another time. The other tool that runs in the functionaries is Watchman. As block signer basically controls all that happens on the sidechain, Watchman controls all that happens on main chain, on Bitcoin. Controls all the UTXOs that are handled there. All those UTXOs have a CSV, so they expire and they need to be swept constantly. And that is a security feature. And also handles all the payouts, which means that it's in charge of scanning the sidechain for payouts and delivering those payouts in the main chain. What we're going to go today is mostly up until the block signer part. Watchman is a bit more complicated, and it's a bit more requires a bit more knowledge. So we're trying to keep today a bit more simple. So yeah, those are the two parts that we have open source last week, block signer and Watchman, and that's what we are going to start reviewing today. Chase, am I okay to share?
Yes, sir. It's all you. And just a reminder for the audience, if you have questions during all this, just leave a comment in the text box bottom right, and we'll get to it. There'll be some downtime, maybe a minute or two during the demo for various reasons. And so, we can try to get to those as we go along here.
Okay. So yeah, as I mentioned, the plan is to start with an empty container, so we can demonstrate that there are no gimmicks, nothing. It's just the way the code is working. So I'm gonna even start by installing the necessary packages to build. Obviously, MC, just because I'm a fan of MC. Git, Rust, Cargo, some Devel requirements, and tools to kill and look for processes, but that's it. So nothing really fancy. There we go. So once that is installed, we are just going to clone the repo that was published last week. Clone and build. Any questions so far? Am I going too fast, too slow? Is it boring? Let me know. Okay, silence is good, I guess.
Pablo, this may be a good time to talk about DynaFed.
Okay, perfect.
And maybe, the code that was made public last week, right? It does interact with DynaFed and gives a little bit more transparency to that. So maybe talk about that relationship and then DynaFed as a whole as we wait for this to load.
Yep, that sounds good. So when the Liquid Network started 5 some years ago, the signers for the block generation and the signers for handling the Watchman, the Federation wallet, they were fixed, and there was no way to change them. And even though it was good enough to start, it wasn't sustainable. So that's how Dynafit came to be. The idea is to be able to let the network transition the signers, or even the structure of the signatures, right? It could be from 11 out of 15 to 12 out of 16, or even to reduce the members. Up until now, we've only been using it to swap keys that needed to be changed, but we haven't used it to alter the structure, but it could be done in the future. The idea is that for 2 weeks, or actually for 2 weeks worth of blocks, the functionaries propose a transition to a new set of signers, and everybody who agrees with that accepts the block. At the end of the 2-week period, it's according on if the proposal has enough blocks, that new consensus becomes that new proposal becomes the consensus for producing new blocks and to handle the wallet. That means that the old keys are no longer valid, and that all the UTXOs that are handled by the Bitcoin wallet need to be swept into the new federation, because every change has a new Bitcoin address. Which means that is basically one of the reasons that we always tell people that when doing peggings, they need to always use fresh addresses, right? And not store them, and not save them for later usage, because those addresses that belong to the old federation, they cannot be used after 2 weeks after the transition. So it's very important that when someone is doing a pegging, use an address that was fresh, right? In order to avoid getting the funds stuck in the old federation. So let's download Bitcoin. I know I should be checking for the hashes and the signatures and everything. This is just a demo, so we're going for the fast way of doing it. But it's, yeah, I hate myself a bit for doing it this way. It's easier for the demo. I have a set of config files that I created for this. We're gonna look them up later, but they are temporarily in that personal repo. So we're gonna go into that directory, and basically I'm gonna start running the functions. You can see I'm running 2 Bitcoin nodes, 2 Elements nodes, 2 block signers, and 2 watchmen. Right? We're gonna go over the configs in a bit, but let's create some aliases to access them. So for instance, if I run you can see that while creating, I created 102 blocks in order to have some funds to handle on the Bitcoin side. I'm gonna create a wallet so I can access the funds. Yeah, there's nothing there yet. The Bitcoin miner is creating blocks to a public key, to a private key that is basically all zeros and ending in one, and that's the that's the with format of the private key. So now we can see that I have some funds to actually use. In the meantime, we can see that no blocks can be produced yet on the on elements, right? And now a block has been produced, which means that the block signers are actually doing what they're supposed to do. Okay, and we are gonna create a wallet in the elements node and do a get pegging address. Right. What we are gonna do now is send some funds to this address in order to do a normal pegging for the network that we just created. So we are gonna send some funds, 10 Bitcoin. I'm gonna copy this for later. And I'm gonna copy this for later. And we are gonna generate some blocks on the Bitcoin chain to make sure that the transaction we just did is ripe enough so we can claim it. Yeah, you can see that we have 200 blocks already on the Bitcoin side. Now, let's prepare the information for the pegging. Before doing that, let's show that we don't have any balance on the liquid side, and we're gonna claim this pegging. If I pasted everything correctly, this should be it. And here we have a transaction. It hasn't been mined yet. So you can see that the transaction is there. Block signers have already produced 3 blocks. So in a few seconds, we should have the transaction mined. There we go. And it's already in our liquid wallet. In order to peg out these funds, it'll require what's called the pack list, which is the peg out authorization keys, and it'll require initializing a wallet to actually be able to understand that pack list and to send the funds back to the main chain. So we are not going to touch that for today, but basically the idea for that would be doing something like send to main chain, no address because it's calculated automatically, and we'd say like 5 Bitcoin. It's gonna complain that it's not initialized. That's exactly what we want, but that's what we need to do in order to be able to peg out. So any questions so far before we get into show a bit of the config files?
Yeah, it looks like there's a few in the chat here. I'll just read them to you.
Yeah, please.
Question, what base image are you starting from?
I'm using a base image for Rocky Linux 9, because that's what I normally use, but It could be anything that supports Rust. I haven't tested in other ones. We normally use CentOS or Rocky for everything, but it shouldn't be important which one.
Second question. Is it 101 confirmations on main chain to claim the peg in on the side chain side?
Yes. Right. It's basically the same rule as miners. We try to use the same rule as the miners have to claim the fees. So basically, make sure that they are no reorgs that did. Okay. Any other question?
Just those two so far.
Okay, good. Perfect. So as I mentioned, I love using MC, so let's dig into that. Bitcoin chain is config is fairly simple. We are using a REST network. Obviously, we are not going to use real funds for this. Allow RPC, open the RPC port, and connect to the other Bitcoin node that we are running. The other one is exactly the same with a different set of ports. Right? Nothing really fancy here. Elements. Let's look in here. Here things are a bit more interesting. The base config is fine. This validate pegging is something that we really encourage people to use even in prod network, which means that when you're running a full elements node, it should connect to Bitcoin when it sees a pegging to validate that the transaction is actually within the parameters and not just blindly accept that what was mined is correct. The functionaries do have this feature enabled, but this is what usually trips users the most when running Liquid for the first time, and they end up setting it to 0 to not validate, and it's not ideal, right? It's not going to change anything functionality-wise, but it's recommended that everybody who is able to run their own Bitcoin full nodes to validate the Liquid chain, basically to keep us honest. This is what Elements uses to query the Bitcoin RPC. You can see that it's the same user and password that we configure in the Bitcoin node. This sign block script looks like a bit of a black magic in here, but if you look in the Strong Federation example in the Elements tutorial, you'll see how this block is produced. Right? It's the validation that Elements is supposed to do in order to determine if a block is valid or not. This is similar, but it's used for handling the Bitcoin wallet. And for the pack, I just created one entry here that it's not valid, that it's good enough for the example. We are gonna go over peg outs and pack entries in another round. Yeah, that's good so far, and going to block signer. Let me check. Yeah, it's still producing blocks. Okay. And you can see in the debug log that it's logging everything, its connections, and all that it's doing. So config.toml. It's configured in debug mode, so we can see more information. Others where it's listening, how to connect to Bitcoin and elements in order to be able to continue with the chain. Let's skip this one for now. Dynafed is already activated, so we don't need to activate it now. And this is where it gets a bit more interesting. Communication keys and signing keys. Communication keys is all the block signers recognize each other not by their names, but by their communication keys. And yeah, the way to generate these keys is also part of the elements tutorial. It's any Bitcoin key that is generated in the tutorial, so you can change these ones without issues. And this is the signing key. Why is the signing key here? Because we don't have an HSM, and that's the limit on what was published last week. Normally, in the real Liquid network, the signing key should be secured inside the HSM, and it would not be in plain text mode anywhere, right? But since we are we only released the functionary code so far, the signing key is in plain text here, and it's and the functionary is using its internal stub replacement of the HSM, which means that what we are doing here is fully functional, but it's not using an HSM to validate the signatures or to generate the signatures and validate things. It's just using the internal replacement and using the keys stored here in text mode. This is basically the duration of the round. And this is the communication key to the public key from this one, and the public key for the signing key. This one is actually public and it's shared by everybody because they should know what the others are signing with. And you can see that since we are in functionary 1, we have information on how to connect to functionary 2. And we are listening in port 1401, the other function is listening in 1402. This information here controls Dynafed. This is we are not doing any Dynafed transition today, but this is the first the first Dynafed state, right? Because it starts in block 0. And you can see that we are creating a network, and the block signer is validated using 2 of 2, right? Threshold of 2 nodes from the keys created by the functionary 1 and by the functionary 2. And the pack list is just there to complete the config, but we are not going too deep into that one today. Watchman structure is fairly the same. RPCs to connect to Bitcoin and elements, not to use a socket to connect to the HSM. Communication keys, signing keys, again, in plain text mode because we are not using an HSM. Communications, and information about the CPE transitions related to Dynafed. And here we can also see what the Watchman descriptor looks like, what we call the FedPeg script. It's, again, a 2 out of 2, but instead of the 11 out of 15 of the Liquid network. But this part is exactly the same, which means after 4032 CSV, the funds can be claimed by the emergency keys. In this case, it's 1 of 3 instead of the 2 out of 3 for the liquid network, but it's the same idea. And that part is a security feature of the liquid network, because in case the network were to go down and in an unrecoverable way, the funds would not be lost because they could be reclaimed by the emergency keys. But in order for the funds not to be available to be spent by the emergency keys, the watchmen sweep those funds constantly in order for the DXOs not to reach the 4032 threshold. And again, the same package, just to keep the configuration complete. And I think that's as far as I was planning to go today. Any questions?
All right. If you have any questions, you can just leave in the chat box or raise your hand and we can bring you on stage. If it's a little bit more easier just to talk and write out and long form your question.
Yeah. Go ahead. Can you, Oscar is saying something. Can you open the mic?
Oh, I think he's just saying hello. There's
Okay.
no question there yet.
No question there.
Yeah. I don't know if you wanted to go into more detail about what the code provides. You know, there was, in general, there were a few bullet points that we covered in the blog post. But from what I understand, you have a more detailed technical follow-up planned.
Yeah.
I don't know if you want to speak on that a little bit, give people some more context on what to expect.
Yeah, okay. What kind of consensus does the code have? No, it doesn't. All this code is pre-PSBT, Oscar, so it's a normal multisig. So everybody provides their part of the signature, and the signatures are all combined in the end by everybody. And so let's talk a bit about that. The block signers, the master of the round proposes the block, distributes the unsigned block, and everybody signs their own version of the block, right? Everybody signs the proposed block, and they send the signatures back to everybody, not just to the master, which means that all of the nodes in the federation, in this case 2 of 2, but in the case of the liquid network, all the 15 receive the signatures. They combine the signatures locally, and they do the submit block to each of their own local elements. Everybody will submit the same block. So even if the functionary that proposes the block goes down, anybody else can still produce the same block. What channels do the functionaries communicate? It's in the it's its own protocol. They connect to each other, as I was mentioning in this part. The listen address and the peer here, they connect over their own protocol, and they validate each other by using the communication key. This is the private communication key, and they validate each other using the public keys in their communication. Actually, they identify each other using the communication keys. Voting before signing, yes and no. Signing means voting that you accept the block, right? Or in the watchman that you accept the proposal. If you don't agree, which happens a lot during Dynafed transitions when not all the functions have been updated, you just stay out of the vote. If there are enough signatures, then the majority agrees, and that's fine. And if there are not enough signatures, then the run fails, and there is no block. We try very, very hard not to propose things that are not going to be accepted by the majority, because we don't want to lose blocks. Chase, I got lost. What did you ask? Oh yeah, I got a note here, pre-commits. There's a part in the protocol that mentions there is a pre-commit threshold, which is when we are about to propose something, we basically the block signers and the watchmen ask the rest if they would support that proposal. So it's part of the controlled pre-signing. Chase, can you repeat? I got lost.
Oh, sorry. Yeah, I didn't see Oscar's questions there, but I was just trying to segue into maybe wrapping it up by going into a little bit more of the
code
aspects, and then speak about your upcoming post, kind of the follow up to the blog entry.
So this is what we released. The main parts here are block signer, the code that is running right now, watchman controlling the Bitcoin side wallet, and there are a couple of other tools here that are not technically necessary, but we could release them without breaking anything internally. So a tool that we use to update the HSM, a tool used to initialize the HSM, parallel port, which is a rewrite of the old version of parallel port that was in C, which is basically, since the HSM is connected through a serial port to the functionary side, parallel port is basically what parallelizes the communication of block signer and watchman to the HSM and to its counterparts. It's not needed for what I was showing today, but it's an idea of how to show people how the functionary sides communicates with the HSM. There are some internal grades here that are used both by block signer and watchman. That's why they are included. And that's mostly it.
There's one more question in the chat here.
Yeah.
How fast can a sidechain produce blocks?
That's a good question. It's mostly related to the communication and how fast they can communicate and agree with each other. In CI, we have, I don't know, rounds that are basically, I don't know, 2 or 3 seconds because everything's running locally. If you have a network that communicate that communicate that fast, they could produce that amount of blocks. Their own HSM. So basically, they'd have to override some of the crates. There's 2 ways to do it. One is looking at parallel port and understanding what goes in and out of the communication and implementing the other side. And the other way would be to look at the functioning code at the internal implementation of the HSM simulation, and basically write their own implementation of that. The functionary code has what we call the stub, which is the internal implementation of what an HSM would do blindly without as many validations as a real HSM. But they could implement that. They could override that. They could implement their own HSM using this code.
Sorry, one more question here. Is this a fork or same source as Liquid?
That's
a good question.
Yeah, the plan is to. This is a snapshot of what's been the internal version of Git, right? And as we update the functionaries, we'll update this snapshot, right? The idea is to keep it always showing what's running on the functionaries. We're not publishing the internal Git, but the plan is to have this be updated constantly as the functionaries are updated. So the idea there is that if people were to create a PR for that code, it wouldn't go directly there. We could certainly use it, but we take it internally and then publish it as the next part of the next release. Yeah, exactly. Yeah, some of the things that we'd like to release, but we haven't because they are too tied to the HSM, are basically some of our testing vectors, right? The whole infrastructure that we use for testing, which is something that we'd like to do, but since it's too intertwined with the HSM, we are not able to publish it in a working fashion, right? Basically, everything that we release is working, and we didn't want to show something that doesn't build. So the idea is to be able to use everything that we published.